Just it's not yet recording. I have 1 second now.
Is he still looking for Jeff?
Oh, yeah. Thank you. I'll wait for a second until he's here. Okay, welcome everybody to the Rocky Mountain Mathematical Physics Seminar. Our speaker today is Professor Andrew Hamilton from the Astrophysics Department at CU Boulder, and he will speak about spin 11.1 string theory. Thank you.
Thank you very much, Marcus, and thank you everybody for coming today. A little over 2 years ago, I was in this spot talking about spin 11.1 as a grand unified theory. During the last year, I've spent most of the year thinking about, does spin 11.1 fit into string theory? The answer is yes, it does, but it doesn't agree with any of the canonical string theories. This is the first presentation that I have made, public presentation that I've made on spin 11.1 string theory. Start up by posing the question, why bother with string theory? I think many physicists would agree with me in saying that it is the most promising theory of quantum gravity at the present time. And its great strength is that string theory is a perturbative quantum field theory. There are two kinds of object that have consistent perturbative quantum field theories. One, you're undoubtedly familiar with, the standard quantum field theory that you learn as a graduate student, and that's the theory of particles, which have 1D world lines. The second string theory that is perturbative is that of strings, which are line-like things. They have 2D world cubes. It is well known and often repeated that particle quantum field theory cannot handle gravity because the coupling parameter of gravity has negative mass dimension, and that makes it non-renormalizable. String quantum field theory, on the other hand, automatically includes gravity, which are spin 2 gravitons, encoded as closed uncharged strings. So what was impossible for particle quantum field theory is automatic, built into string quantum field theory. On the right-hand side, you see various Feynman diagrams. This is, for example, a red quark turning into a blue quark as a result of an interaction with a red-blue gluon. This is the string theory version of the same thing. In the string theory version, the strings connect a blue quark to the red quark as a string. The quarks live on the opposite ends of the strings. I'm going to be talking today about spin 11.1 string theory, which is an open bosonic string theory. So the picture that you see in these Feynman diagrams is appropriate for the spin 11.1 string theory. Gravitons are closed loop. Here, for example, is a gluon interacting with a graviton in standard particle quantum field theory. In the string version, it looks like this. The graviton is encoded in a uncharged closed loop. That's the strength of string theory. And I very much I'm an enthusiast of string theory. Otherwise, I wouldn't waste my time on it. But it has its weakness. And in my opinion, and this is just my opinion, the weakness of string theory is supersymmetry. Super is physics speak for fermionic. So you see Superman in the guise of Christopher Reeve, and I well remember as a youth, relative youth, watching this film and being completely entertained by it. And he's holding kryptonite. As you know, every superpower has its kryptonite. And the kryptonite of superstring theory is supersymmetry. Let me remind you what the reasons for supersymmetry are. These are the standard arguments that are given for supersymmetry. I've listed 6 of them down here. I'm going to return to this slide near the end of this seminar with some answers to each of these recommendations, showing why none of them is robust. But briefly, nature has fermions. You and I are made of fermions. Solid bodies are made of fermions because fermions satisfy an exclusion principle. So we don't spontaneously collapse to a black hole or something like that. The second reason is the Coleman-Mandula no-go theorem that says you cannot combine a grand unified theory in space-time in any other way than a direct product. And supersymmetry evades that. Third reason is that the three coupling parameters of the standard model don't quite meet when you extrapolate them up to high energy, but they do meet if you add in supersymmetry. The fourth reason is a reason inside string theory itself, which is that bosonic string theory has a tachyonic ground state. That means a negative mass squared ground state, and that makes it unstable. And that is usually argued as reason to dismiss bosonic string theory. So spin 11.1 string theory is a bosonic theory, and yes, it does have a tachyonic ground state. We'll mess with that later on. Fifth reason given is something that's closer to ordinary quantum field theory, which is that boson masses, scalar boson masses, have a quadratic divergence in quantum field theory in their masses, and that can drive the mass of a scalar boson, like the Higgs scalar, up to very high masses, unless something stops that from happening. And supersymmetry, if it happens at not too far above the electroweak scale, can remove that and allow for a low mass scalar boson such as the observed electroweak Higgs boson. And then number 6, another feature of string theory is that gauge anomalies, which are required to vanish in a consistent quantum field theory, they vanish in standard model, for example. In string theory, they don't vanish unless there is supersymmetry. Okay, I'll revisit those. Two big problems with supersymmetry. The first one is that it predicts symmetries that are not observed. Supersymmetry predicts superpartners. And one of the reasons for building the Large Hadron Collider was to look for superpartners which were expected to be found not too far above the electroweak scale. That's what we were told. And now the Large Hadron Collider has been running at 8 TeV and still no sign of any superpartners. And this has caused some, how should we say, some disaffection amongst string theorists and as well as their critics. Okay, so that's one problem which is well observed, well rehearsed. But the second problem, I think, should be more widely advertised, which is that supersymmetry actually preempts the symmetries that are observed. And this is a mathematical statement. And on this line, I'm showing you the basics of supersymmetry algebra. It involves spinor generators, which come in right and left-handed versions, and the left and the right-handed versions are conjugates of each other. And if you take an anti-commutator of a right and a left-handed spinor, you get a vector thing, which in supersymmetry is identified with the generator of a translation, the momentum vector P. And in the Poincare algebra, translations commute. So P, the anti-commutator of two P's, is equal to 0. On the other hand, Brouwer and Weil showed back in 1935, they knew all about this. If you take two vectors, this anti-commutator of two spinors, that makes a vector. The commutator of two vectors in a Clifford algebra, or geometric algebra, as I like to call them, they produce bivectors. And the bivectors are the ones that we see. There's right-handed bivectors and left-handed bivectors. And that algebra is actually realized in the standard model. And you can see right away by comparing this to that, supersymmetry rules it out at the outset. One of the, of course, supersymmetry does allow, string theory, it does allow gauge forces, boson, but only by patching them on. It's not built in to the subject. Tyler, you know that I've been worried about this for many years and have complained about this for many years. Now I'm going public with it. Spin 10. Back in 1975, shortly after the electroweak theory that Steven Weinberg in 1967 had proposed that the Higgs mechanism would would combine the would provide an electroweak symmetry breaking, and then the Z boson was discovered, and their masses and their coupling parameters was agreed with what was predicted. So there was a lot of excitement. This was the advent of the Standard Model in 1974, and almost immediately people were beginning to ask, physicists were beginning to ask, what about grand unification? The Standard Model is a product U1 cross SU2 cross SU3. This is the electroweak symmetry, and this is the color symmetry. Why not, if electroweak was so successful, why not combine those as some grand unified theory? And there were three that were proposed, and the largest of those was what physicists call SO10. I prefer to call spin 10, which is the more accurate statement. That's the covering group of SO10. It elegantly contains those forces, and spin 10 correctly reproduces the charges of the Standard Model. 2.5 years ago, I explained to you how to think about spinners. Frank Wilczek in 1998 first pointed out that spin 10 can be characterized by a bit code containing 10 over 2 or 5 bits, consisting of 2 weak bits, which I call Y and Z, and 3 color bits, R, G, and B. So this is spin 10. This is spin 10. Where's the camera? The camera can see this, right? So
the camera's on your computer.
What?
The camera is on your computer.
The camera's on my computer. Okay, good enough. Thank you for pointing that out. That's about right. Good enough. So each spinner it's got 5 bits, and each can be either up or down. That's plus a half charge, minus a half charge. Those Y, Z, R, G, B charges are the same as those in the Standard Model, or at least linearly related. There's a hypercharge, there's a weak isospin, and then 3 colors in the Standard Model. A linear combination of those gives these 5 bits. Okay. This is the right-handed neutrino. All bits up. If I flip what I call the Y bit, it changes it to the left-handed neutrino. If I flip what I call the Z bit, it turns the neutrino into an electron. This one's a right-handed electron. And if I flip the Y bit back up again, it becomes the left-handed electron. For quarks, here's a red quark. It's got 1 red bit up and the other bits down. And it looks to me like it's a left-handed, the Z bit makes it a down quark, and it's left-handed because these are opposite. If I flip it, the Y bit, I make it into now a right-handed thing. And if I flip the Z bit, I make it into a up quark instead of a down quark. Beautiful. Much prettier than what you may have learned in your quantum field theory class. This is the way it should be taught in quantum field theory. I want to persuade you that it's obvious that spin 11.1 is what you should combine space and time and spin 10 in. So each of these 2 to the 5th spinners, each can be either up or down, each is itself a Weil spinner. That is a massless chiral spinner with 2 degrees of freedom. Those Weil spinners transform under the Lorentz group, which of course is part of the space-time group. And so there are actually not just 32 spinners, there are 64 spinners. And the smallest spinner group that contains 64 fermions, 2 to the 6, is spin 11.1. You have to have 1 more bit, which I've colored gold. I call it the T bit. It has to be a time-like bit. It's the most important of all of the bits. Without it, there would be no time. Okay, the second obvious reason is that spin 10 chirality, right or left, coincides with Dirac chirality. Remember I said I flipped the Y bit and I turned it from right to left? Well, notice spin 10 chirality counts whether the number of up bits is odd or even. Yep. So that's spin 10, but it's the same as direct chirality because this one flips the direct chirality. There's a coincidence. So there is a redundancy between these two things. And that means allows one to embed the Lorentz group, spin 3-1, and spin 10 group in spin 10 in only not 10 plus 4 dimensions, but 12 dimensions. So you add one extra bit, which is the time bit. And now you have all the 64 spinners of one generation of the standard model. And there they are. Now, this coincidence of chiralities is a mathematical statement. It's a coincidence of pseudoscalars. Chirality is the eigenvalue of the pseudoscalar. And in a Clifford algebra, the pseudoscalar is the product of all the vectors of the algebra. For example, the Dirac algebra, there are 4 gamma matrices. Product of those 4 is the Dirac pseudoscalar, commonly called gamma 5. The 12-dimensional pseudoscalar is likewise the product of all the 12 vectors of the spin 11-1 algebra. And they coincide. Is it a coincidence? In the standard model, the answer is yes, it's just a plain coincidence, because I have to assume that space-time and the grand unified geometry are, according to the Coleman-Mandula theorem, they have to be separate. Take this seriously? I think you should. It's a mathematical coincidence. Let's take it seriously. Okay, so you go through a lot of work. This took a lot of work to figure out what the algebra is, but indeed it works. The game is, can I express the Dirac vectors, which are the generators of the Dirac algebra, in terms of these 12-dimensional spin 11-1 things? And the answer is yes. And this is the equality. You see that the Dirac time vector this is actually the same as the time vector in the spin 11-1. You see it's got a little t bit there. The minus is a imaginary and the pluses are real. So whenever you've got spinners, you have a natural complex structure, and with every bit there is associated a complex vector, so 2 real vectors. And so I've called them gamma k plus minus, plus being real, minus being the imaginary, and that runs over the 5 bits. The 6 bits. That is the 12 vectors. Can I just write that down? No, I have to check that the algebra works. The inner products and Lie algebra of these space-time vectors, the Dirac vectors, as expressed on the right-hand side, they are precisely those of the Dirac algebra. Tick. Number 2, the standard model algebra is generated by a subset of bivector products of these 12 vectors. So they're bivectors. Yeah. It's a subset because the standard model is a subgroup of spin 10. And the key point here that makes this all work is that the Dirac and standard model algebras are mutually commuting subalgebras of the spin 11-1 Clifford algebra, consistent with the Coleman-Mandula no-go theorem. The Coleman-Mandula theorem does not say that you cannot combine a grand unified group except as a direct product with space-time group. It says only that the symmetries that you observe in the standard model must commute with those of space-time. And that is all that is required by the Coleman-Mandula theorem, and that is satisfied here because the Dirac and standard model algebras are commuting subalgebras. And notice that SU5, which is not a part of the standard model, but it is a subgroup of spin 10, it does not commute with this particular Dirac algebra. So SU5 is ruled out as a grand unified theory. Again, it took a lot of work to figure this out, and there is a non-obvious trick that allows this algebra to work, which is to modify all the imaginary vectors by multiplying them by a phase factor times the color pseudoscalar. You may remember that the color pseudoscalar came in here as part of that pseudoscalar, the total pseudoscalar, that passes into a boost part and a rotation part. So that So that pseudoscalar also generates a spatial rotation in the 1-2 plane. That's a serious trick. Spin 11.1 is highly predictive. It's highly constrained. So you can ask, okay, if I go from the standard model to spin 11.1, is there anything in the middle? And the answer is yes. And it's the Patti-Salam group, which is one of those other grand unified group. It's a subgroup of spin 10. And if you calculate, which you can using well-established techniques for calculating the running of the coupling parameters in the standard model, you find that spin 11.1 predicts unification to the Patti-Salam group, spin 4 cross spin 6, at 10 to the 12 GeV, where the 3 coupling parameters meet in a certain combination here. There they are, meeting at 10 to the 12 GeV. And this makes a bunch of predictions, which you may think, well, that's fairly useless. It's up at 10 to the 12 GeV, but that's not my fault. Okay, there are predictions analogous to the predictions for Z bosons and the W bosons. There are relations. Then, yeah, I guess I missed out talking about the Higgs field. The Higgs field is built into the spin 11.1 algebra. Notice that one of the factors in the Higgs field is one of these gamma T things, which does not, it's a time vector. It's not part of the spin 10 algebra. It is part of the spin 11.1 algebra. It's part of a 4-component couplet with exactly the correct transformation rules as the Higgs multiplet proposed by Steven Weinberg. That's the successful one. So it's built in. It's not, does not have to be added in. It's already there. Grand unification. There's also a grand unified, a grand Higgs field, which they call T, because it's T after all. And that also is built into the algebra. It's a bivector product of the real and complex parts of the time vector, again, modified by this magic color pseudo scalar. And that is predicted to unify at 10 to the 15 GeV, where these two. Notice that the unification here doesn't require that 3 coupling parameters meet at once. Rather, what happens is first the hypercharge gets absorbed into combination of the right and left weak groups, and then subsequently grand unification happens when the color and the combined weak group merge at 10 to the 15 GeV. On to string theory. It's 12 dimension. I tried very hard to make this work in 11 dimensions, which is M theory, or possibly 12 dimensions with F theory. And Tyler, you remember sometime last July, me giving you a paper which said string 11.1 doesn't work with string theory. And you told me at that time, that's a very depressing conclusion. Can't you do better than that? And I went home, and that night, my brain said, Andrew, you're going the wrong direction. Don't believe in M theory. Don't believe in F theory. Believe in what you see, which is the standard model and general relativity. Make a string theory. If it disagrees with what other people have said, fine. That's nature talking. Okay. So I've already talked about 3 + 1 and 10 internal fitting inside 11 + 1 dimensions. Yes, it works. It continues to work in string theory. And one can ask the question, how do these vectors, these 12 vectors which form this internal 10-dimensional compact manifold, how do they transform? If I go back to this, for example, I can take one of these things, this is the imaginary Z vector, and ask how it Lorentz transforms. And the answer is it anti-commutes with gamma 3 and it commutes with the others, so it transforms like gamma 3. And you can do that same exercise with all the other vectors. And the conclusion is that the 4 weak vectors Lorentz transform like the Dirac vector gamma 3, and the 6 color vectors transform like the Dirac vector 1. So in other words, the Calabi-Yau, okay, so we haven't got to that. So the 4 weak and 6 color vectors, together they form a 10-dimensional compact complex manifold, a D10 brane, if it's string theory, right? This is going to be a D brane. And it is that D10 brane which carries the 2 to the 6 spinors of spin 11.1. And that color pseudoscalar turns out to provide the complex structure that is required by a complex manifold. So the weak and color gauge fields of the standard model are carried by bosonic open strings whose ends attach to the D4 and D6 color subbranes of the fermionic D10 brane. And after symmetry breaking to the standard model, that fermionic D10 brane becomes a 10-dimensional Calabi-Yau five-fold. I remind you that a Calabi-Yau n-fold is a complex manifold of n complex dimensions with SUN holonomy, and its big feature in string theory is that it carries 0 internal energy momentum, so can count as something that can be everywhere in space-time at the present time and not make any contribution to the energy momentum. That's the big thing about Calabi-Yau manifolds. If I click on this, it's going to open a Mathematica program, which, Tyler, you will be very familiar with, right? You remember doing this? So I'm going to evaluate your notebook. By the way, if you want to write tech in Mathematica, this is how you do it. Did you know that?
Can't see your Mathematica.
What?
You need to share something different.
Okay, let's just unshare and share this again. Screen share. There we go. Share. Brilliant. I wish I could get rid of you, but never mind.
You're still sharing the presentation slides.
Oh. That's the one. There we go. Okay. So I think I ran this. If you want to do tech in Mathematica, you can, in case you didn't know. Isn't that beautiful? Now those ugly fonts, you can turn them into beautiful LaTeX fonts. Okay. This is the original. This is originally from Andrew Hansen in 2011. And they're actually just Fermat surfaces, which are solutions of a simple complex polynomial. And the game is to get a threefold, you need n equals 3 plus 2, so you need 5 things. So this is a Calabi-Yau threefold, lives in 6 dimensions. This was Andrew Hansen's original thing, and they're quite cute, aren't they? So we want to go to 10 dimensions. So this is a Calabi-Yau five-fold, and there's a couple of buttons which Tyler made. First of all, he wanted to show you that actually the Calabi-Yau manifold probably exists at tiny scales so that you can't see it. But now we've blown it up. And you can rotate the Calabi-Yau manifold internally without messing with the space-time. And you can rotate the space-time without messing with the Calabi-Yau manifold. In case you think this is a bit miraculous, it's straightforward in this version of spinors, which is to say a rotation in space-time is a bodily rotation of the whole lot. Isn't that simple? That's extraordinarily simple. And if you want to turn a particle into an antiparticle in spin 11.1, you flip the t-bit. How simple can you be? Beautiful. Onward. So this is a color string, which is attached to the Calabi-Yau manifold, which transforms like gamma 1. And this is a weak string, which is attached to the attached to the 4-dimensional thing. The two together form the 10-dimensional Calabi-Yau manifold. And if I stop this I can rotate this around, and that works. And then the pièce de résistance, here you put it all together. You can rotate this. You can rotate the internal Calabi-Yau manifold along the phi direction or along the theta direction. Yes.
So you said these are Calabi-Yau five-fold, so the singularities which look here then appear by projection, but are originally not there, or
Oh, the little glitch is here. That's just Mathematica. It's a smooth object.
yes, okay, then that was my question. It is a smooth object, but what looks here like a singularity comes because you can visualize only two-dimensional stuff.
Well, this is a two-dimensional cut through a. Okay, it's a three-dimensional projection
Yes,
of a four. Okay,
of a higher
so
dimensional thing, and
it's a
therefore
higher dimensional
yes,
thing.
therefore
Yes.
singularities look
Yes.
and appear in the projection.
Yes.
That's a normal thing. That's
I'm sorry, I cannot visualize
yeah, that's
higher dimensions,
Yeah.
and this last little button makes that thing do its thing. Okay, so I'm going to go back to sharing my hopefully other screen, my presentation, which is this one. Okay, so this is posted. You saw it at the beginning. And if you press on any of these, you get that Mathematica program if you're jealous of Tyler's program. Okay, so there were a number of magical things. At least I thought that they were magical in discovering this spin 11.1 string theory. And I have to say, this has been a voyage of discovery for me. I didn't know what was going to happen. You just have to follow the logic and see where it takes you. It turns out that the heterotic string theory, which was introduced by the Princeton String Quartet, Gross et al., in 1985, they proposed one of the standard string theories, heterotic string theory. Heteros means both. It means it's a combination of bosonic and fermionic strings. And the cancellation of anomalies, of conformal anomalies, requires bosons to live in 26 dimensions and fermionic strings to live in 10 dimensions. So how do you combine them? You have to compactify 16 of the 26 dimensions. 16 of the 26 bosonic dimensions. And they did that by compactifying on a 16-dimensional manifold, which was a self-dual torus of E8 cross E8 or SO32. That's two of the standard string theories. Heterotic E8 cross E8 or heterotic SO32. E8 is the largest of the exceptional groups. I followed that same structure. Spin 11.1 is a bosonic string theory. It's not a fermionic string. It doesn't have supersymmetry. It's got 12 dimensions. I need 26, so I need a 14-dimensional torus to compactify it on. And the group that spin 10 gives me is actually not spin 10 itself. It's a somewhat larger group. I call it G, it's actually other people call it G2 in 10 dimensions, which is the group of multivectors of grades 2 mod 4, not just bivectors, but also hexavectors, yes, which is a larger group. Why do you need that? Because the Lorentz transformations are actually all 6 vectors. So you need to have not just 2s, but 6. And that group is U16, and SU8 cross SU8 is a subgroup of U16. The other two parts of U16, there's 2 U1 factors that go in there. One of them is just the IRGB spatial rotation. The other one is, I won't bother to tell you about, but it also plays an important role. Anyway, that is the group that is provided, and it has 14 dimensions. Thank you very much, nature, for providing the right number of dimensions. But the other thing is it has to be self-dual. That is to say, there is a symmetry in spin theory, in string theory, which exchanges the time coordinate, the string time coordinate, with the string spatial coordinate. and there must be a symmetry under that, and that requires a torus which is self-dual. Again, Gross et al. Talk about this in great detail, and I just followed them. To make SL32 self-dual, you have to introduce a spinor root, and the same thing works with SUN tori. Mathematicians, you should know this stuff because it's not, as far as I can see, in the literature, but it is there. This is the simplest of the special unitary toruses. SU3 torus, it's got rank 2, so it's two-dimensional. So I can draw it on a plane. You're used to a torus which has got 90-degree generators, giving you a flat torus. In the case of SU3, the two generators are at 120 degrees and not 90 degrees, and they produce a you periodically identify them, so these blue points are periodically identified. Anyway, you can get a self-dual torus in this fashion, and you end up with a gauge group, which is that. That was one of the magic pieces. There's a second piece of magic which astonished me. In string theory, one usually starts out with, let there be Minkowski space, and let's do quantum field theory. Of course, that's always what one does. But I don't have flat space. In particular, what nature is presenting to me is this Calabi-Yau fivefold, which is decidedly non-flat. And that's a bother. Okay, first of all, so how do you deal with this? First of all, the 26 dimensions consist of 1 + 1 spacetime, 10 fermionic internal dimensions, and then the 14 dimensions of the bosonic, 14 torus. The other two spatial dimensions disappear as a result of a gauge transformation. You take a gauge transformation, you can rotate the space so that the t-bit is up, and you have it. You've got rid of 2 dimensions in that fashion. So first of all, the string metric is a 2x2 symmetric metric. So it has 3 degrees of freedom. You use the 2 degrees of coordinate freedom in the time and the space string coordinates to eliminate 2. You get a conformally flat metric. And then you can Wick rotate those coordinates into a complex plane. And it's a conformally Euclidean complex. So you're doing a Wick rotation to Euclidean space, but it's now a complex space. And in curved space-time, the string action, which is the Nambu-Goto action, this is what this string equation looks like. That's what emerges from the action. In Minkowski space-time, the connections all vanish. These are Christoffel symbols, and you just get this equal to 0. And the solutions of that are linear combinations of Z and Z bar modes, right and left moving modes in string theory parlance. But there's another way to get simple solutions of this. In a curved complex manifold, the wave equation also has open strings, which are all right moving, functions only of Z. So if that is the case, then this disappears, the dz tilde of the x disappears, and you end up once again with a simple equation of wave equation. And then you can just follow the usual string quantum field theory, which you can read about in the textbooks. So you expand the coordinates in this z, and it's a Laurent expansion, actually with a log z in there as well. And then you quantize that, and these things end up being those are the quanta of the torus, and these are so-called gauge Kaluza-Klein modes. And the reason this works in curved space is that the Z can be treated as if it were a Fourier mode, as if it were in flat space. This works only for open strings. It does not work for closed strings. It does not work for heterotic string theory, but it works for us. Third magic thing, gauge and gravitational anomalies vanish. Gauge anomalies can happen in quantum field theory, and they must vanish. Gauge anomalies in quantum field theory destroy the gauge invariance, the classical gauge invariance, and they must be avoided. The standard model has the property that the gauge anomalies vanish, and any viable theory has to do so. These anomalies arise from fermion loops. So it's got a fermion loop. This one is in 4 dimensions, in even space-time dimensions. It's n+1 vertices attached to vertical lines. So these are gluons. So this diagram is appropriate in 4 dimensions. In standard supersymmetric string theory, gauge anomalies vanish only for gauge groups of dimension 496. And those are E8 cross E8 or SO32. Now, supersymmetry does not allow chiral spinors. It demands, the algebra demands Majorana spinors, in spite of the fact that the observed spinors of nature are chiral, not Majorana. But supersymmetry requires that. And there is a magical cancellation of anomalies between the fermions and not other fermions, but multivector boson fields, in particular free-form fields. And that mathematical miracle, discovered by Green and Schwartz in 1984, is what precipitated the superstring revolution. I must say, my jaw dropped in reading that paper. This is miraculous. And when I see miracles performed before my eyes, I have to believe in the higher power. Spin 11.1 string theory. The vanishing of gauge and gravitational anomalies is trivial, almost trivial anyway. The point is that if fermions and also bosons come in chirally matched sets, then the gauge anomalies vanish between the opposing sets. Indeed, there's a right-handed part of SU8 and then there's a left-handed part of SU8. This contains the right-handed spinors, the left-handed spinors, and there's also a conjugate representation which contains their anti-spinor parts. So that was nice. Generations, one of the big puzzles of modern physics. Generations, where do they come from? There's 3 generations of fermion, but only 1 generation of bosons. So plainly 3, is it a symmetry? It's not like the bosonic symmetries, it's something else. And in string theory, there's long been a proposal that the generations arise from the Calabi-Yau manifold. So in strings with fermions living on a compact internal manifold of a appropriate type, the number of generators is equal to half the absolute value of the Euler characteristic of the compact manifold. And the first Calabi-Yau threefold discovered by Yau himself with 3 generations was then immediately provoked a very influential paper by Candelas and company in 1985 to take 10D E8 cross E8 heterotic string theory, compactify it to 4 dimensions on a 6-dimensional Calabi-Yau threefold. That's where all the Calabi-Yau thing came from. That was the starting point. And there have been many investigations of Calabi-Yau threefolds and some of 4-folds, and practically almost nothing on Calabi-Yau 5-folds. So there's some piece of work to do for the mathematicians. This on the right-hand side, this is a plot of the multiplicity of Calabi-Yau threefolds. On the bottom axis is the number of generations going from -500 to 500. And these are Hodge numbers, which are topological numbers. This is their sum, this is their difference. And this is on a logarithmic scale. You can see it going up to, so there's about 1 million. These are, each is a point. Each one represents a point with a certain discrete set of Hodge numbers. They're all integers. So there's 1 million or so Calabi-Yau manifolds with certain one distinct pair. There's a lot of them. Tachyon. Yep. String, spin 11.1 string theory has a tachyonic ground state. There it is. M squared equals -2 over L squared. L is the string scale. So this is a hugely negative mass squared tachyon. It's up at the grand unified scale. Okay, so if you don't like tachyons, you're done. Spin 11.1 string theory is ruled out. However, I would like to bring to your attention the fact that this grand Higgs field, which is built into the spin 11.1 algebra and does the ground symmetry breaking, it matches the properties of the tachyonic ground state. It's a space-time scalar, it has 0 standard model charge, and it is unstable by the Higgs mechanism. In the standard model of cosmology, the vacuum energy is decayed through successive Higgs-mediated symmetry breakings to the present time. Okay, so the standard model of cosmology involves inflation, which solves the horizon problem, 60 E-folds of inflation at least required to solve that problem, and then the grand symmetry is broken. That's the picture. And then in spin 11.1, there's then Padi-Salam symmetry breaking, and then electroweak symmetry breaking. And here we are now going into a dark energy dominated phase where the vacuum energy is 120 orders of magnitude smaller than the Planck scale. I promised you that we would revisit the weakness of string theory thing. So here are these 6 arguments. Nature has fermions, I agree with that. Back in 1985, it was not known how to do string theory without supersymmetry. But in 1995, Joel Polchinski told us about D-branes. D-branes are boundaries upon which boson open strings can terminate, and D-branes can carry fermions. So in 1995, you should have revisited what you had thought was true in 1985. No, you don't need supersymmetry. Number 2, I've told you about how spin 11.1 obeys the Coleman-Mandula theorem because the Dirac and internal algebras always commute. I've told you how spin 11.1, the 3 coupling parameters meet it by 2 separate steps without any fine tuning. I've argued that in cosmology, the tachyonic ground state is maybe the Higgs field. I don't know if that's true, but it seems to me you can put 2 and 2 together. That vacuum state of ground unification was unstable. String theory, bosonic string theory has an unstable ground state. Put those 2 things together, maybe they're telling each other. And then about this fermion boson infinities cancel each other. I just want to pose the question, can you really apply standard quantum field theory to something like the electroweak Higgs boson, which after all is the boson associated with the vacuum energy electroweak symmetry breaking, which in a stringy thing is kind of different from ordinary standard quantum field theory. So maybe that needs to be thought through. Anomalies vanish, yes, but in spin 11.1, anomalies vanish because it's chirally balanced. Problems. Supersymmetry predicts symmetries that are not observed, preempts symmetries that are observed. Spin 11.1 is not supersymmetric, and it possesses by construction the symmetries that are observed. I'm almost done here. I'm just going to read this. The complicated DNA of earthly life, you may remember this from 2 and a bit years ago on the same slide, is a language written with 4 letters, T, A, C, and G. It may be that the complicated DNA of the universe is encoded in the labyrinthal convolutions of the folded up dimensions and the stringy fields that coil them. If spin 11.1 is correct, then the letters of the DNA of our universe are the 6 bits T, Y, Z, R, G, and B. I'm done here. There's only one thing I really want to say. This is really a summary of my talk. I want to say that spin 11.1 may already be ruled out because the predicted energy scale of ground unification at 10 to the 15 GeV is less than the lower limit of 4 times 10 to the 15 inferred for spin 10 by Ping et al. From the Super-Kamiokande lower limit on the proton lifetime. However, that was a calculation for spin 10. It seems to me one should redo the calculation in the specific context of spin 11.1 and take carefully what happens at the Padi-Salam symmetry breaking. It may not be abrupt, as I have assumed, it may well be curved. And that would raise the ground unification scale. I am done. Thank you very much.
Thank you very much, Andrew, for the nice talk. Are there questions?
What would the experimental signatures of decaying tachyonic Higgs fields be?
I think we've already seen those signatures. If I'm right, which is to associate them with those tachyons with the Higgs fields that break the symmetries, and starting from the cosmological, starting from grand unification, it is widely thought in cosmology that the universe began in this inflationary epoch driven by the energy of the grand vacuum. And so that is the observational evidence. I don't think you need observational evidence because the observational evidence is already there. What is needed is a theoretical linking of that observational evidence to tachyons in string theory. That's the missing piece. I haven't done that, but it seems to me that is a place that needs to be explored.
Yeah.
Without going into the more exotic energy scales, since you're building it without starting with Minkowski space, shouldn't you check the more, you can replicate the more classical quantum field theory results?
Before doing string theory, this was a talk about string theory. I'm assuming that classical quantum field theory works.
But you don't build it, you only have two space-time dimensions, and then you're tacking on the other ones with the Calabi-Yau.
I have 4 space-time dimensions. They coexist. Okay, when I rotate the Calabi-Yau manifold, I'm basically rotating the whole thing. This is a rotation of that Calabi-Yau manifold. Here I am rotating it.
Yeah.
So the 2 extra dimensions, they're already contained. There are 3+1 large space-time dimensions.
Yes.
But that 3+1 plus the 10 internal, they are accommodated inside spin 11.1.
But shouldn't that have some sort of physical significance?
I don't get your question because kind of everything has physical significance. Everything I've talked about has physical
So the
significance.
standard is you start with these 4 and then you add little tiny dimensions, right?
Yes.
But now you're saying that they're sort of entangled. These big ones and small ones are interact in some way.
They are flexing. I showed you in the mathematical program how you can rotate the Calabi-Yau and independently rotate the space-time dimensions.
That seems very fundamental and should be able to be checked at some scale, right?
If the Calabi-Yau dimensions are tiny, which they have to be, otherwise they would have been discovered already.
Sure.
The canonical wisdom is that the scale would be the characteristic scale of the string scale, which would be up at grand unification. So it's up at 10 to the 16 GeV, which is 10 to the minus 30, whatever it is.
No chance.
Things.
Okay.
But I kind of agree. This is a very well-defined model. It's highly predictive. Unfortunately, yes, most of its predictions are being made up at super high energies. I'll give you one prediction, for example. It says that the Majorana mass, which the grand Higgs field gives the right-handed neutrino its Majorana mass because it gives it a T charge, and only the right-handed neutrino can have a T charge because only it is a singlet of the standard model. All the others have other charges, and they cannot flip between particle and antiparticle, but the right-handed thing does. Okay, the prediction is it has a mass of order the Patti-Salam scale, which is 10 to the 12 GeV. If you then ask, what is the prediction? If you go from 10 to the seesaw mechanism through the Dirac scale, which is about whatever it is, 100 GeV or something, you get to observed neutrino masses. It just happens.
Okay. Further questions? No, then let's thank the speaker again. Thank you. Yeah. Next week, James will speak on the non-commutative torus. Thank you.